Welcome back to our lectures on subRiemannian groups. We are in the process of discussing first-order necessary conditions for length minimizers. In the previous video, we saw that every geodesic parameterized with constant speed is a critical point of the extended endpoint. We started to calculate the differential of the endpoint map. Now we will continue, and we will prove that every geodesic parameterized with constant speed will satisfy one of two possible equations, either the normal equation or the abnormal equation. Actually, a curve can satisfy both equations with different parameters. Let's see.
Let's recall the settings of subRiemannian Lie groups to then deduce some conditions for their geodesics. So we have G, this connected Lie group. We have delta, a polarization or subbundle of the tangent bundle, subbundle, let's say of rank M. And then we fix x1 up to max m, a frame for delta, and we declare it orthonormal. In other words, we are taking these vectors to be left invariant. Let's start left invariant and orthonormal. So left invariant. So therefore we have a left invariant scalar product on delta. Now, how can we parameterize curves? So for any element in the space, let's call it omega, namely the space of L2 functions on 0, 1 valued in Rm, we can associate a curve gamma, let's call it gamma of u, which is a curve from 0, 1 value in the group G. And that is the curve such that, okay, it starts from the identity of the group, and the derivative time t, this is going to be a vector at gamma t. So let's see it as the push forward by left translation of gamma t of a vector at the identity, and the vector at the identity is the sum of ui t xi at 1. Okay, of course I could just write the x are left invariant, right? So I can just really write ui of xi at gamma t. But it's good to have both point of views, okay? But you see, this vector and this vector, they really have the same norm. In fact, we can calculate the length of gamma as the integral of the norm of the vector u. So ui square, so we write t sum, forgot the sum, sorry, sum ui t square dt integrated between 0 and 1. In the previous video, we saw that minimizing the length is equivalent to minimize the energy. This up to reparametrization, where the energy, let me recall, which is actually the energy of a control, this is how we define it, is 1/2 the norm of ui square t dt. So in other words, this is 1/2 the square norm, and this is the L2 norm of this function u. Okay, and also last time we considered the map, the extended endpoint map, which is a map from the space of controls, valuing the group, and the first entry is the endpoint, times r, second entry is 1/2 of the norm u square in L2, is the energy. Okay. Last time we also calculate the differential of the endpoint map. Okay. Now let's see also what is the differential of the energy. That's very, very simple. So, so the energy is 1/2 the norm square of u. So let me just write it 1/2 the scalar product between u and u. And this map is a quadratic map. And its differential at u is what? Okay. I claim that this is, let me write in a new page, this is the differential of the energy at u applied to v. I claim that this is the scalar product between u and v. Why is this so? Okay. So what is, by definition, we have to consider the energy of u plus epsilon v and take the derivative in epsilon for epsilon equal to 0. Okay, let's write this. So the energy, as we said, is the scalar product of u plus epsilon v with itself. And this is, so this is the norm square of u. Forgot that 1/2, divided by 2. Plus, then there is the double product. So it's scalar product between u and v times epsilon, plus norm of v squared divided by 2 epsilon squared. Okay, epsilon equal to 0, and of course the derivative at 0 is this function here. Okay, so we proved this fact. So this is the differential of the energy. Okay, so let's put together the differential of the energy with the differential of the endpoint map that we proved in the previous video. Okay, I write it as a proposition. So the differential of the extended endpoint map at a control u is, okay, it's the map. So this goes from omega into the tangent and u of g times r. Remember that omega is just L2, so it's a vector space. So the differential is just the tangent space is the vector space itself. And this assigns to every v. Okay, last time we saw that this can, the differential of the endpoint map is the right translation by gamma of u. Okay, sometimes I'm writing gamma u of 1, sometimes n u, but this is just the same thing. Okay, so it's the right translation, push forward, of the vector that is the integral between 0, 1, 1 of the adjoint, the gamma u of t, vt in dt. This is the first coordinate, and the second coordinate is, as we just calculate, is the scalar product between u and v. Okay. Something else that we also discussed last time was that if gamma u is a geodesic parameterized by a multiple of arc length, is a length minimizing parameterized by multiple of arc length, obviously parameterized by at constant speed, then g and u tilde is not surjective. Because otherwise, by the inverse mapping theorem, one could find a local inverse and decrease the energy, maintaining the same endpoint. Okay, so now we have an explicit expression for this differential, okay? And now let's see what it means that this map is not surjective, right? It just means that the image by this linear map of this linear space is a subset, is a proper subset of this space, okay? So let's deduce, okay. If the differential of the extended endpoint map U is not surjective, then, okay, by definition, the end tilde U applied to omega, this is a subset, but it's a proper subset of the tangent gamma U G times R. Okay, now let's see this space. We can see it as the push forward by the right translation, so the right translation by gamma 1 of the okay, maybe I should write translation, and okay, in the second component I should also put something, 1 comma the identity in R. Let me just write identity of R, which actually should be called 0, of the tangent at the identity. Okay, why I want to write it like this? Because I have the expression for the differential with this this map here. Okay, so up to bringing back this vector via the inverse of this map at the identity, what I can conclude is so this was equal. Then what I can conclude is that I have a proper subspace. How can I say that you have a proper subspace? I can find a covector, so a linear map. Let me write a linear map from G star times R, so from on G times R to R, such that this covector is different than 0, and lambda 1, lambda 0 applied to the image up to deleting this part here is 0. So integrating between 0, 1 at gamma v, comma uv, this is equal 0 for all v in omega. In other words, like if this space is a proper subspace, then I can find a vector, a non-zero vector that is orthogonal. Okay, so like you can see this as if you want to fix a scalar product on G times R, I'm just saying that exists a constant, an orthogonal vector. Okay, so I can find a non-zero orthogonal vector to the whole image. And here I didn't put the right translation because I bring back the identity. Okay, let me write this scalar product. So in other words, so i.e. Lambda 1 applied to 0, 1 add gamma v plus lambda 0 uv is equal to 0 for all v in omega. So this is a condition that a control U of a geodesic must satisfy for every V. Okay? Now there are going to be two cases according whether this gamma 0 can be chosen to be 0 or not. Okay. There are two cases. Lambda 0 is different than 0, or lambda 0 is equal to 0. Let's do the first case. Case lambda 0 different than 0. This is called normal case. Okay. Up to dilating by a constant, right? You can multiply here by a factor, right? All of this by a factor. We can assume that this number is 1. So up to dilating lambda 0, we assume lambda 0 equal to 1. So the equation becomes lambda 1 integral between 0 and 1 add gamma v plus vu equal to 0. Okay, now this is true for all v in omega. Now let's choose properly some v's. Choose properly some v. Now I'm going to choose I fix a vector, let's say E0, or let's say let's fix one of those initial vector EI in G, and also I fix a time t in 0, 1. It's called t0 in 0, 1. And I take a sequence of v, let's call it vj, converging, not in L2 because as a distribution, to the delta Dirac at the point t0 multiplied by ej. This as distribution. And vj are in L2. Okay? Then what happens? What happens is that this term will converge to the will converge to the scalar product between ej and u at time t0. This one here instead will converge to add gamma t0 ej. So what we get is the following inequality. So we get the equality lambda, I call it lambda or lambda 1? Lambda 1, okay. So lambda 1, 1. Lambda 1 add gamma t ej plus ej ut is equal to 0. Okay. Now remember that ut is the sum of ujt xj. And therefore what we have up to, okay, what we get is that the uj at t is equal to minus lambda 1 add gamma t ej. This is an equation that we call normal equation. So here, okay, this ej are just the vectors at the xj at the identity. So ej is xj at 1. So this is the normal equation, and first implication of the normal equation is that is the following. Remember, gamma is a continuous curve. So this right-hand side is a continuous function. So this means that this function that was just in L2, a priori, is actually continuous. Okay? So U is continuous, not just in L2. But if it is continuous, a gamma, U is the derivative of gamma. So from this equation, we get, okay, so gamma continuous, let's say C0, implies U C0. But U is the derivative of gamma, which implies that gamma is C1. But from the normal equation, this means that U is C1. This is called a bootstrap argument. And because of you're linking the derivative with the function, so the only function for which the derivative has the same regularity of the function itself are the C infinity functions. So this implies that gamma is a C infinity curve. The functions satisfying this equation are called normal curves. So we proved that normal curves are always smooth. Okay, curves satisfying the normal equation are called normal curves, and are smooth, and are C infinity. Let me rephrase. So normal curves are the curves that satisfy the normal equation. And the normal equation is gamma dot t equal the sum over I from 1 to m, where m is the rank, a covector lambda applied to the adjoint gamma applied to ei times the vector xi at the point gamma t, where E1 up to EM is an orthonormal basis for the horizontal space for delta at 1, and the vectors xi at the point G is the left translation of the vector ei. Okay, this is the left translation by G at 1. Okay, so now let's go back to the other case where the covector, the second part of the covector, is not necessary, is equal to 0. So let's recall what we were discussing. I recall what maybe I should have given a name. Let's call it the extremal equation. So was the existence of lambda 1 and lambda 2 that was annihilating the image of the extended endpoint map plus lambda 0 uv equal to 0. Right? So we got this equation for every control u, giving gamma u energy minimizer. Okay. We already discussed the case where lambda 1 is different than 0, up to dilating lambda 1 equal to 1, and we have the normal equation, right? Now let's consider the case instead when lambda 0 is equal to 0. We will call this the abnormal case. Okay, so this part, we don't have it, so we have this is equal to 0. Okay, so let me rewrite it again. So there exists some lambda that is a covector and now this vector has to be non-zero, because the second part is for sure 0. And we have that lambda of the integral between 0 and 1 of add gamma v is equal to 0 for all v control in L2. Now I want to improve this this equation like we did in the normal case. So now what I do, I fix a vector, a constant vector, v in the horizontal space of the identity, and also fix some time, t bar, in 0, 1. And what I would like to do, I would like to consider the distribution given by the delta function v bar delta at the time t bar. Okay, so this is as a distribution. Okay, so it's a mass measure. So this is not a function in L2, but we can approximate. So now we're going to consider a sequence of Vj in omega such that Vj converge, so these are in L2, but they converge to the Dirac, the delta, as distributions. So it's like bump functions. We are considering bump functions where this is the time t bar and the value is v bar. Okay, so now what happened about to this equation? Right? So let's rewrite it. So what we have, 0 is equal to lambda integral from 0, 1 to add gamma vj, and this will converge to lambda 0, 1 add gamma v bar delta t, t bar. So this is, t bar is fixed. When I integrate, this is just the value of the function at the gamma v bar, sorry, put gamma at t bar v bar. So what we get is what we call the abnormal equation, and is lambda add gamma v equal to 0 for all v in the horizontal space of the identity. This is a subset of the algebra. So it's actually, this is the same of delta intersect the algebra. Seeing as tangent at the identity. Okay, so now this is called the abnormal equation. Differently from the normal equation, we cannot deduce that gamma is smooth. Okay, so warning. This equation does not imply smoothness. And moreover, I'm not going to say anything about this and about why it's true, but we know that there are abnormal cases and examples of abnormal geodesics that are not normal curves. Actually, I don't want you to think that this classification as normal and abnormal is a dichotomy, right? So there could be curves that are at the same time normal curves and abnormal curves. They satisfy both equations. Let me stress why this is true. I write it as an observation. So the fact is that as we get to this to the classification as normal and abnormal, we were considering the image of the differential of the extended endpoint map at U, where U was an optimal control, the control of an energy minimizing curve. Okay, so this was a proper subspace, but the codimension of this space, codimension of this subset inside the tangent space gamma 1 times r, this is at least 1, but might be bigger, so may not be 1. Okay, might be right, and therefore the covector that we chose, to be orthogonal to this image is not unique, or may not be unique. Hence, it may happen that a curve is both normal and abnormal, namely satisfies both the equation, the normal equation, and the abnormal equation. Okay, this is all for now about energy minimizers on groups. If you like the video, you can let me know by clicking the like button. This will also suggest the course to other people. If you want to see more videos on subRiemannian geometry, please subscribe to the channel clicking below. Bye.